Hi guys, welcome to a session on complex analysis. Today we'll be doing a crash course on complex analysis, and basically I'm gonna talk a little bit about complex numbers. Now we know that the complex number is denoted by the basic complex number is denoted by z is equals to x plus iy. We say that this is in rectangular form. Okay, it's in rectangular form. So in the beginning of complex analysis, first year you did a complex number in rectangular form, how to multiply it, how to how to divide it, how to use its complex conjugate. Today I'm not gonna cover all of that since we covered it in our first year calculus, but if you need help with that, you can go and watch the videos for calculus 1. Okay, now this is what happens. Now I'm just interested in changing this from rectangular form to exponential form. Okay, now there's a relationship between the rectangular form, x is equals to r cos of theta and y is equals to r sine of theta. Do you see that we can write x with respect to r and theta, and we can write y with respect to r and theta? Now if you can check, in our z we've got x which can be written as r cos theta plus y which can be written as r sine theta. Okay, now we take out r, that is common. We have now cos of theta plus I sine of theta. Okay, now this does not mean that we have written it in exponential form. We just wrote it in in polar form. So this is our complex number in polar form. In polar form, guys. Okay, now this term here is what we call Euler's theorem or Euler's formula. Let me just say it's Euler's formula. Okay, formula. And Euler's formula says that this whole thing, cos of theta plus I sine of theta, is just equals to e to the I theta. You can prove that, guys. Okay, so I'm not gonna prove that. So yeah, so now this hence give us that r, and then in the inside there we can just replace that with this, then we can have r e to the I theta. Okay, so this is what we call a complex number in exponential form. Okay, it's pretty simple, it's pretty basic. We don't have much to speak about. Okay, now in exponential form we've got this r which is called the modulus, and the modulus is given by r is equals to the absolute value of z, which is just x squared plus y squared. They come from our complex number here, x squared plus y squared. Okay, now that is our modulus, and we have this theta which is called the argument of the complex number. Okay, and the argument is always given. Okay, now there is the principal argument and there's an argument. Okay, now the principal argument is just a capital letter theta, which is given by the argument of a complex number. Now these are two arguments. Okay, this is what we call the principal argument, and the principal argument, this one, theta, the capital theta, is always between negative pi and a positive pi, where negative pi is not included. It's very important for you to note that. Okay, negative pi is not included. Okay, now let us continue. Then there is an equation that you need to know which says that the argument of z is equals to the principal argument of z plus 2 pi n, where n is equals to 0 plus minus 1 plus minus 2 da 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 da. Okay, so this is what happens when we want the argument given the principal argument. Actually, let me get an example for this idea that we have down here. Okay, now let me just move this. Okay, let's have an example here. Find the argument, not the principal argument. Find the argument z, argument of z, of the complex number -1 minus I, which we can assume that it's z because they said we should find the argument z, but let us leave that one for now, which lies in the third quadrant and has a principal argument. Now we're given the principal argument. Okay, now let us solve this, guys. The principal argument of -1 minus I is given by -3 pi over 4. We all agree on this one, guys. Okay, now we do not need to find the principal argument because the principal argument is given to us. Now we need to find the argument. Okay, now remembering that the argument of z is equals to the principal argument of z plus 2 pi n, where our n is equals to 0 plus minus 1 plus minus 2 and da da da. Okay, therefore the argument of -1 minus I will be equals to -3 pi over 4 plus 2 pi n, where our n is equals to 0 plus minus 1 plus minus 2 da 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 da. Okay, so this is what we have as our argument of z. But somebody might say to me, our angle cannot be negative. Okay, and I will say, oh, true. Let us look at something. We are told that this thing lies in the third quadrant. Okay, this is our x, this is our y. Practically, we say this is the real part of the complex plane, and this is the imaginary part of the complex plane. Okay, imaginary part of the complex plane. Let me remove this. Now they say this lies on the third quadrant, meaning that the angle from here to here is -3 pi over 4, which in essence, that argument of -1 minus I lies between this and -pi, which is true because this is less than that. Okay, oh, bigger than that because it's a negative. It's bigger than that. Now this is what happens, guys. We can find an argument or the angle that lies on this side that extends until here, and that angle is what we call the coterminal angle. Okay, the coterminal angle is just an angle that moves in the anti-clockwise or the counterclockwise direction, and it terminates at the same terminal arm. Okay, this is the terminal arm, guys. Okay, this one. Okay, now when I say they terminate at the same terminal arm, I mean like they end at the same terminal arm. Okay, now this is what happens. The angle that I'm gonna have here practically is just going to be this -3 pi over 4 plus 2 pi. Okay, now that angle is 5 pi over 4. Okay, why? Somebody might ask why. Because 2 pi can be thought of as, so I'm gonna have this plus 2 pi can be written as 8 pi over 4. Okay, so you see that the denominators are the same, so I'm gonna have 8 pi minus 3 pi, which this is just 5 pi over 4. Okay, now this angle 5 pi over 4 is just the coterminal angle that I was talking to you about. Okay, this 5 pi over 4 is the angle that is gonna form here. This angle is gonna be equal to 5 pi over 4. Okay, oh my, it's running out there. Now we can say now, since we want to have it as a positive, the argument of -1 minus I is equals to 5 pi over 4 plus 2 pi n and where our n is equals to 0 plus minus 1 plus minus 2 da 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 da. Okay, so we can say that our n is an element of integers. It really doesn't matter. Okay, now they say we should find the argument. So if you write the argument like this, and write it like this, is still the same. Okay, because okay, now guys, under in the comment section below, please tell me what is the solution for sine of negative 3 pi over 4 and the solution of sine of 5 pi over 4. So for us to see if whether these two angles are equal to one another, they're both going to be negative, because I can see already with this negative sign, and they both lie in the fourth quadrant. In the fourth quadrant, tan is positive, sine is negative. Even with cos, guys, cos of negative 3 pi over 4 should be equal to cos of 5 pi over 4. Then we can say that those two angles are coterminal angles to one another. Now, I don't want to extend too much on these things, guys, okay? I hope you understand it, and if you don't, please do let me know in the comment section below. For now, let us just have another example. Let me not find an example where we have something like this. Let me find an example where we have to change from rectangular to exponential form. Okay, now we're saying that write minus 1 minus I in exponential form. Okay, guys, so minus 1 minus I is the same question that we just did now. Okay, now looking at this, guys, we need two things only. Remember that our complex number in rectangular form is just given by x plus iy, which in exponential form is going to be given by r e to the I theta, where r and theta are the unknowns. But if you can remember well, the principal argument that we given in the previous question said that it's a capital theta. Actually, capital theta is equals to negative 3 pi over the 4. So we're gonna use that. Okay, we're gonna use the solution we found previously. Now, when they say that we should find this, let us find our value of r. Our value of r will be given by the coefficient of this one, minus 1 squared, plus the coefficient of I. The coefficient of I is negative 1 as well. Okay, this will be the square root of 1 plus 1, which is just the square root of 2, because 1 plus 1 is 2. Now, we do have this, but we don't have the small letter theta. The small letter theta is given by that argument that we found in the previous question. Okay, now when we want to write this in exponential form, we're going to say that minus 1 minus I will be equals to r, which is the square root of 2, e, I, and theta is going to be minus 3 pi over 4 plus 2 pi n, where that is our argument, not our principal argument, our argument, where our n is equals to 0 plus minus 1 plus minus 2 da 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 da. Okay, so basically we have written our complex number from rectangular coordinates to exponential form. Okay, so I don't know if whether I do make sense or what, but for now I have given you both the ideas and I've given you examples on both ideas. So let's have the second part where we'll explain, or we'll go further in this thing of changing to exponential to rectangular and all of that. If you came this far, guys, please hit the like button, please subscribe, guys, and if this helps, guys, please share with other people. For now, thank you very much for staying with me. Thank you.